Hello there, and welcome to the Sleeping Physicist. If you're someone who likes to unwind by thinking about the quiet mechanics behind clouds, winds, and changing skies, you're in the right place. Tonight, we'll let our attention drift gently into real physics and real observations about the atmosphere around us. Some of what you'll hear may sound familiar, but the way it fits together can be surprisingly elegant. And if you enjoy these slow journeys into how the universe behaves, you're welcome to like and subscribe. But for now, get comfortable, let your body rest, let your thoughts wander, and let's begin. How does sunlight end up becoming wind, clouds, and storms? Every moment of weather begins the same way, with sunlight arriving at Earth after a long journey through space. This light does not arrive gently everywhere at once. It pours down most directly near the equator and glances off the surface at higher latitudes, spreading its energy thin. When sunlight reaches the ground or the ocean, it is absorbed and turned into heat, warming the surface layer by layer. This heating is not dramatic or sudden, but it is relentless, happening every clear day, building tiny differences that quietly accumulate. If you pause for a moment and think about where you are listening from, you might notice how different surfaces respond to that sunlight. Pavement warms quickly, grass stays cooler. Water changes temperature slowly, holding on to heat long after the sun has set. These differences are not cosmetic. They matter because heat is energy, and energy always moves when it can. The atmosphere exists in constant contact with these warmed surfaces, and it cannot ignore them. As the ground warms, the air just above it warms as well. Warm air expands, becoming slightly less dense than the air around it. This change is subtle, but physics is patient. Lighter air begins to rise, not because it wants to, but because gravity and pressure leave it no other option. Cooler, denser air nearby takes its place. This exchange is the first quiet motion in what will become wind, clouds, and eventually storms. At this stage, weather is not yet complicated. It is simply the atmosphere responding to uneven heating, doing what all physical systems do when energy is added unevenly. It begins to move. The sun provides the energy, Earth's surface redistributes it, and the air responds automatically. There is no intention, no chaos yet, only a simple physical necessity unfolding. That uneven heating is not an accident of weather, but a consequence of Earth's shape and motion through space. Because the planet is curved, sunlight strikes different regions at different angles. Near the equator, the same amount of solar energy is concentrated into a smaller area, warming the surface efficiently. Toward the poles, that energy is spread across a wider surface, arriving weaker and more diffuse. This simple geometric fact quietly establishes a permanent temperature gradient across the planet. Earth's rotation adds another layer. As the planet turns, every location moves through day and night, warming and cooling in a steady rhythm. Land responds quickly to this cycle, heating rapidly during the day and releasing heat just as quickly after sunset. Oceans behave differently. Water absorbs heat more slowly and releases it reluctantly, storing energy and redistributing it through currents. This is why coastal regions experience gentler temperature swings, while inland areas feel sharper extremes. These differences create a patchwork of warm and cool regions that is always shifting but never disappearing. Mountains intercept sunlight and airflow. Deserts reflect and radiate heat efficiently. Forests trap moisture and shade the ground. Snow and ice reflect sunlight back into space. Each surface slightly alters how energy is absorbed and released, adding texture to the planet's thermal landscape. The atmosphere sits atop all of this, pressed gently against a surface that is never evenly warm. Because heat cannot remain uneven forever, energy begins to flow from warmer regions toward cooler ones. This is not weather yet in its familiar forms, but it is the quiet setup. Temperature differences are being maintained by sunlight and reshaped by Earth's rotation, ensuring that the air above has no chance of staying still for long. Air often feels invisible and weightless, but it is a real physical substance, made of molecules moving constantly in every direction. When air is warmed from below, those molecules move faster and spread slightly farther apart. The air becomes less dense, meaning the same volume now contains less mass. Gravity still pulls on it, but the surrounding cooler air presses more strongly, nudging the lighter air upward. This upward motion is not dramatic at first. It begins as a slow, almost imperceptible lift, like warm air rising from a sunlit road. As the air ascends, it enters regions of lower pressure. With less pressure squeezing it, the air expands. Expansion requires energy, so the rising air cools as it stretches outward. This cooling is not caused by mixing with cold air, but by the simple physics of expansion itself. Meanwhile, cooler air nearby responds automatically. Denser air sinks, sliding in to replace the rising air. This sinking air warms slightly as it is compressed by higher pressure below. Together, these motions form a vertical circulation, a gentle overturning that continuously trades warm air upward and cool air downward. The atmosphere is quietly sorting itself by density, moment by moment. At this stage, nothing needs to be named or classified. There are no winds yet, no clouds, no storms. There is only air responding to heat exactly as physics demands. Warm air rises, cool air sinks. The motion is slow, steady, and unavoidable, laying down the invisible scaffolding upon which all weather will soon organize itself. As air rises in one place and sinks in another, it quietly reshapes the weight of the atmosphere above the surface. Where warm air ascends, there is slightly less air pressing downward, and surface pressure decreases. Where cooler air sinks, more air accumulates near the ground, and pressure increases. These pressure differences are small, but the atmosphere is vast, and small differences spread across great distances matter. Air does not tolerate imbalance. When pressure is higher in one region and lower in another, air begins to move sideways. It flows from higher pressure toward lower pressure, not as a decision, but as a mechanical response to unequal forces. This horizontal movement is what we experience as wind. It begins gently, almost unnoticed, as air slides across the surface, filling in where air has risen away. You can imagine this motion like a slightly tilted surface covered in fine sand. Even a shallow slope is enough for grains to begin drifting downhill. In the atmosphere, pressure differences create that invisible slope. The steeper the difference, the faster the air accelerates. Calm days are simply days when the slope is shallow. Windy days are when the pressure gradient sharpens. This sideways flow links distant regions together. Air warmed in one place does not stay there. It moves, carrying energy with it, redistributing heat across the planet. Vertical motion creates pressure differences, and pressure differences create wind. By this point, weather has found its first organized form. The atmosphere is no longer just rising and sinking. It is now sliding, flowing, and beginning to trace large patterns across the surface of Earth. As air begins to flow across the surface, another influence quietly shapes its path. Earth is not standing still beneath the atmosphere. It is rotating, carrying the ground, the oceans, and the air itself eastward at different speeds depending on latitude. Near the equator, the surface moves faster than it does closer to the poles. Air that begins moving north or south carries with it the rotational speed of where it started. As this moving air travels, it no longer lines up perfectly with the ground below. To someone standing on Earth, the air appears to curve. In the northern half of the planet, moving air bends to the right. In the southern half, it bends to the left. This is not because a force pushes it sideways, but because motion is being observed from a rotating frame. The air continues straight in space, while the Earth turns beneath it. This effect becomes noticeable only over large distances and long times. A gust of wind in your backyard will not curve perceptibly, but winds that travel hundreds or thousands of kilometers are gradually redirected. Instead of rushing directly from high pressure to low pressure, air begins to spiral, sliding along pressure differences rather than cutting straight across them. This bending organizes the atmosphere. Broad belts of prevailing winds form. Large rotating systems emerge, where air circulates around regions of low and high pressure instead of collapsing into them. Without Earth's rotation, weather would still exist, but it would be simpler and more violent, dominated by direct, chaotic surges of air. Rotation brings structure, turning simple flow into vast, graceful patterns that wrap around the planet. As air moves and curves across the planet, it rarely travels alone. It carries water with it, not as droplets at first, but as invisible vapor. When sunlight warms oceans, lakes, soil, and even leaves, water molecules gain enough energy to slip free from liquid into air. This process of evaporation does not just move water. It stores energy inside the vapor itself, quietly and efficiently. This stored energy is easy to overlook because it does not change temperature right away. Evaporating water cools the surface it leaves behind, while the air absorbs the energy without feeling warmer. The energy becomes hidden, tucked into the motion of water, molecules now drifting through the atmosphere. Air that contains water vapor is therefore carrying more energy than dry air at the same temperature. When that moist air begins to rise, the story deepens. As rising air cools through expansion, there comes a point where it can no longer hold all of its water vapor. The vapor begins to condense back into liquid, forming tiny droplets. When this happens, the hidden energy is released back into the surrounding air. The air warms slightly, even as it continues to rise. This release of energy acts like a quiet engine. It makes rising air more buoyant than it would otherwise be, allowing it to climb higher and persist longer. Moisture does not create motion by itself, but it strengthens motion that has already begun. In this way, water vapor becomes a powerful amplifier in the atmosphere, transforming gentle circulation into something more dynamic, more structured, and eventually capable of forming clouds and storms. As rising air continues upward, cooling steadily as it expands, the invisible water vapor within it reaches a physical limit. Cooler air cannot hold as much vapor as warmer air, and when that limit is crossed, water molecules begin to gather. They cling to tiny particles already floating in the air, forming microscopic droplets or ice crystals. This is the quiet moment when a cloud is born. A cloud is not a solid object, nor a single thing. It is a region where countless tiny droplets are suspended, light enough to remain aloft because the surrounding air is still rising, or gently turbulent. The height at which clouds form is not arbitrary. It marks the level where temperature and pressure conditions finally allow condensation to begin. In this way, clouds act like visible tracers, revealing the invisible structure of the atmosphere. As condensation continues, more hidden energy is released. This extra warmth slows the cooling of the rising air, allowing it to rise higher than dry air could. The cloud deepens vertically, building layer upon layer. Some clouds remain thin and spread out, their upward motion gentle and brief. Others grow tall, reaching far into colder regions where ice forms and gravity begins to assert itself. When droplets collide and merge, they grow heavier. Eventually, rising air can no longer support them. They fall, becoming rain or snow, returning water to the surface. This is not a separate process from cloud formation, but its natural continuation. Air rises, cools, condenses, releases energy, and finally gives water back to Earth. Clouds are the visible signature of energy and moisture moving together, moment by moment, through the atmosphere. When rising air, moisture, and released energy reinforce one another over a wide area, the atmosphere begins to organize itself on a much larger scale. Storms are not accidents or disruptions. They are structured responses to excess energy concentrated in one place. Warm, moist air near the surface rises persistently, drawing in surrounding air to replace it. This inflow feeds the system, allowing it to sustain itself for hours or even days. Inside a storm, air moves both upward and outward. Near the ground, air converges toward the low-pressure center, carrying heat and moisture with it. Higher up, that air spreads outward, losing energy to colder surroundings. The storm acts like a conveyor, lifting energy from the surface and redistributing it higher in the atmosphere and farther away. This is how the planet sheds excess heat efficiently. Thunderstorms represent this process in its most compact form. They grow tall because rising air is strong and focused. As long as warm, moist air continues to arrive at the base, the storm remains active. Once the supply weakens, sinking air and rainfall cut off the inflow, and the storm collapses. Nothing mysterious ends it. The energy source simply runs out. Larger systems like cyclones and hurricanes follow the same physics, scaled up across hundreds of kilometers. Rotation, moisture, and pressure differences combine to create long-lived structures that transport enormous amounts of energy from warm regions toward cooler ones. Seen this way, storms are not acts of violence by nature. They are the atmosphere doing essential work, restoring balance through motion, rain, and wind. As air circulates across the planet, it does not mix evenly everywhere. Large bodies of air tend to form over regions with similar surface conditions, becoming warm or cold, dry or moist as a whole. These air masses can travel long distances while retaining their basic character. When two different air masses meet, the boundary between them becomes a front, and weather often changes quickly there. At a front, denser air behaves differently from lighter air. Cold air, being heavier, tends to slide beneath warm air, lifting it upward. This lifting is forced rather than gentle, and it often happens along a long, sloping surface where the two air masses press against each other. As the warm air is pushed upward, it cools, clouds form, and precipitation becomes likely. The sharper the contrast between the air masses, the more active the weather tends to be. Warm fronts work more slowly. Warm air advances toward cooler air but cannot easily push it aside. Instead, it glides up and over the cooler air in a gradual ascent. Clouds thicken over a wide area, and rain or snow can fall steadily for hours. The physics is the same as before, air rising, cooling and condensing, but the pace and structure are different. Fronts are not lines drawn on maps for convenience. They are physical zones where energy, moisture and momentum are being rearranged. They mark places where the atmosphere is actively adjusting to differences that cannot persist. When a front passes, the air you are standing in may be replaced entirely by air that formed hundreds or thousands of kilometers away. Weather changes because the air itself has changed. By the time air masses meet, storms form and fronts pass. The atmosphere has become a tightly connected system where every motion influences the next. Yet despite being governed entirely by physical laws, weather becomes difficult to predict far into the future. This is not because the rules are unknown, but because the system is exquisitely sensitive to small differences. A tiny change in temperature, a slight shift in humidity, or a subtle alteration in wind speed can grow over time, reshaping the evolution of the atmosphere. Two nearly identical starting states will slowly diverge, then separate completely. This sensitivity means that even perfect equations cannot deliver perfect long-term forecasts, because the atmosphere never begins from a perfectly measured state. Still, this behavior is not randomness. The air does not move arbitrarily. Every gust, every cloud, every storm follows directly from pressure, temperature, moisture, and motion. The unpredictability comes from amplification, not disorder. Small causes lead to large effects through continuous interaction across scales. In this way, weather sits at a delicate boundary. It is fully physical and fully lawful, yet endlessly variable. The same sun rises each day. The same planet turns beneath the sky. And yet the atmosphere responds with infinite variation, not because it is unstable, but because it is alive with motion, always adjusting, always redistributing energy, always doing exactly what physics allows, and nothing more. Because the atmosphere connects motions across many sizes at once, from tiny turbulent swirls to planetary wind belts, its behavior unfolds across overlapping scales. Small eddies mix heat a few meters above the ground, while vast circulation cells move energy between the equator and the poles. These scales are not separate. Energy cascades between them, flowing upward and downward in size, linking the immediate air around you to patterns that encircle the globe. This connection is why forecasts are reliable in the short term and uncertain in the long term. Over hours or a day, the large structures dominate, and their evolution is constrained by momentum, heat, and moisture that change only gradually. Over longer spans, the smaller motions have time to grow, feeding back into the larger flow and reshaping it. The atmosphere remains lawful at every step, yet the pathway it takes becomes increasingly specific, dependent on details too fine to ever be known completely. Still, there is a quiet order beneath the variability. Seasons return because solar geometry repeats. Prevailing winds persist because rotation and heating remain. Storm tracks favour certain regions because land, ocean and mountains guide the flow. Weather may surprise from day to day, but climate patterns endure because the underlying physics does not wander. Seen this way, weather is not noise layered on top of order. It is order expressed in motion, responding continuously to energy, arriving from the sun and constraints imposed by a rotating planet. Each cloud, each breeze, each shifting front is a local answer to a global question that never stops being asked. How can this energy move, and where must it go next? All of this motion exists for a single, persistent reason. Earth receives more energy from the sun than it can keep in one place. The atmosphere is part of the system that redistributes that energy until it can be released back into space. Weather is the visible trace of that redistribution happening continuously, without pause. Warm regions lose energy by sending it poleward through moving air and evaporated water. Cold regions gain energy as that air arrives, releasing heat and moisture. Clouds reflect some sunlight back to space while trapping some heat below. Winds mix layers that would otherwise remain separate. Every part of the atmosphere participates in this balancing act, guided by gravity, rotation and thermodynamics. Nothing ever fully settles. As soon as one imbalance is reduced, another emerges. Day follows night. Seasons shift the angle of sunlight. Surfaces warm and cool at different rates. The atmosphere responds again and again, adjusting its flow to match conditions that are always changing. Stability is temporary, motion is permanent. This is why weather never truly stops. Even on the calmest day, energy is moving quietly, invisibly, through air and water. The sky may look still, but the physics never rests. The atmosphere remains alert to the smallest difference, ready to turn sunlight into motion, and motion into the endlessly varied patterns we experience as weather. Above the surface where we live, the atmosphere is quietly arranged into layers, each shaped by how temperature changes with height. Near the ground, air is warmed from below by contact with Earth's surface. Higher up, that influence fades, and different processes take over. This vertical structure matters because it determines how easily air can rise, how clouds grow, and how storms either flourish or fail. When the air near the surface is warmer than the air above it, rising motion is encouraged. A lifted parcel of air finds itself lighter than its surroundings and continues upward, expanding and cooling as it goes. This is an unstable arrangement, one that favors convection, cloud growth, and energetic weather. The atmosphere in this state is primed for motion, ready to convert small disturbances into towering structures. At other times, the situation reverses. Cooler air lies near the surface, capped by warmer air above. In this case, rising air quickly becomes denser than its surroundings and sinks back down. Vertical motion is suppressed. Clouds struggle to form and the atmosphere settles into a layered calm. This stability can trap moisture and pollutants near the ground, creating haze and fog, while the sky above remains deceptively clear. These layers are not static walls, but flexible zones shaped by radiation, mixing, and motion. During the day, sunlight warms the ground and deepens the lower layer, where air is free to rise and mix. At night, the surface cools, and that layer collapses into a thin, stable sheet hugging the ground. Weather responds to this daily breathing of the atmosphere, expanding and contracting with the cycle of light and dark. Higher still, the atmosphere reaches a region where temperature stops falling with height and begins to rise. This transition acts like a soft ceiling. Rising air spreads out beneath it, unable to climb further. Storms flatten at this boundary, their tops spreading into wide anvils. This limit is not imposed by weather itself, but by how sunlight and ozone interact far above, shaping the thermal structure of the sky. Within these layers, waves ripple through the air, much like swells moving across the surface of the ocean. When air is displaced upward in a stable layer, gravity pulls it back down, but momentum carries it past its starting point. Oscillations form, transporting energy horizontally. These atmospheric waves can shape cloud patterns, organize winds, and even influence where storms initiate, all without producing obvious turbulence at the surface. The interaction between layers is where much of weather's subtlety resides. A storm may struggle to grow if stable air aloft resists rising motion, even when the surface is warm and moist. Another day, a small break in that stability allows air to surge upward explosively. Forecasting often hinges on understanding these vertical relationships, not just surface conditions. Through all of this, the atmosphere remains governed by the same simple principles. Air rises when it is lighter, sinks when it is heavier, and moves to relieve imbalances. What changes is how those principles are expressed when layered, constrained, and continuously adjusted by radiation from above and heating from below. The sky becomes a three-dimensional structure, not just a horizontal flow. Standing beneath it, we experience only a thin slice of this complexity. A breeze at ground level, a cloud drifting overhead, a sudden change in temperature. Yet each of these sensations is connected to vertical motions extending kilometers upward, shaped by layers we cannot see but whose effects we feel. Weather is not only something that happens across the landscape, it happens upward, through depth, through structure, through a constantly negotiated balance between motion and restraint. In this way, the atmosphere resembles a living column, responsive at every level. Energy enters from the sun, is absorbed and redistributed, rises and spreads, cools and sinks, constrained by layers that both enable and limit motion. The result is not confusion, but a dynamic order that expresses itself as endlessly changing skies. Even when the weather feels quiet, the structure above remains alert, layered, and ready, holding within it the next adjustment that physics will inevitably require. All of this structure and motion would remain abstract if it could not be observed. Yet the atmosphere leaves traces everywhere, and physics becomes tangible through measurement. Thermometers register temperature, but what they truly capture is molecular motion slowed or accelerated by energy exchange. Barometers sense pressure, the accumulated weight of air pressing downward, revealing where air has risen or sunk elsewhere. Each instrument is a quiet translator, converting invisible forces into readable signals. Weather balloons rise through the layered sky, expanding as pressure drops, carrying sensors that record temperature, humidity, and wind. As they climb, they trace the vertical structure directly, revealing where air is stable, where it is primed to rise, and where motion is capped. Radar sends pulses of energy into clouds and listens for echoes, detecting rain not by sight, but by how droplets scatter waves. Satellites watch from above, measuring infrared, radiation, tracking moisture, and mapping winds by following drifting clouds. None of these tools invent weather. They simply listen carefully to what physics is already doing. From these observations, patterns emerge. A region of falling pressure hints at rising air. Increasing moisture suggests energy waiting to be released. Winds shifting with height reveal rotation and shear, conditions that can organize storms or tear them apart. Forecasting is not prediction in the dramatic sense. It is an ongoing attempt to describe the present state of the atmosphere as completely as possible, then allow physical laws to carry that state forward in time. This is where chaos quietly re-enters the story. The atmosphere contains more detail than can ever be measured. No network of instruments can capture every eddy, every gradient, every subtle variation. Forecast models begin with the best possible snapshot, then compute how air should move, warm, cool, rise, and sink. Over short times, large structures dominate and the forecast holds together. Over longer times, small uncertainties grow and the path diverges. Yet even here, physics does not fail. What changes is not the validity of the laws, but our ability to specify initial conditions with infinite precision. The atmosphere remains obedient to thermodynamics and motion, even as our descriptions blur. Forecasts express probability, not because the future is undecided, but because our knowledge of the present is always incomplete. On a human scale, this limitation becomes part of the experience of weather. We plan around likelihoods, not certainties. A chance of rain reflects real physical possibilities, branching from nearly identical starting states. The sky overhead embodies those branches, choosing one outcome through continuous interaction, not sudden decision. Despite this uncertainty, there is deep reliability beneath the surface. Heat will still flow from warm to cold, air will still rise when it is lighter, moisture will still release energy when it condenses. No forecast ever violates these principles. What varies is how, when, and where they combine. Standing beneath the sky, it can feel as though weather happens to us. But from the perspective of physics, weather is something we are immersed in, sharing space with a fluid system that extends far above and beyond us. The breeze on your skin is part of a circulation shaped by Earth's rotation. The cloud overhead reflects energy exchanges spanning kilometers. Even the calm is an active state, maintained by balance rather than absence. In this way, weather becomes a conversation between sunlight, surface, air, and motion, translated into experience through sound, temperature, and light. Physics does not sit behind the scenes. It is present in every sensation, every shifting shadow, every change in the wind's direction. The atmosphere speaks continuously in the language of forces and flows, and weather is simply what it sounds like when we listen closely. Beneath all the motion in the sky, the surface of Earth continues to shape weather in quiet but decisive ways. The atmosphere does not float freely above the planet. It rubs against land and water, exchanging heat, moisture, and momentum every second. This boundary layer, the lowest part of the atmosphere, is where physics becomes tactile, where weather touches skin, leaves, and buildings. As wind moves across the surface, friction slows it down. Air closest to the ground moves more slowly than air above, creating a vertical shear. This shear generates turbulence, a constant mixing that blends heat and moisture upward while bringing faster-moving air downward. The rougher the surface, forests, cities, mountains, the stronger this mixing becomes. Smooth surfaces like open water allow winds to glide with less resistance, preserving speed and direction. Heat exchange here is immediate. Sun-warmed ground transfers energy directly to the air above, while cooler surfaces draw heat out. Moist soil and vegetation add water vapor through evaporation, enriching the air with stored energy. Dry ground limits this exchange, favoring heat buildup instead. These differences can alter local weather profoundly, steering storms, sharpening temperature contrasts, or calming the air altogether. Over oceans, the boundary behaves differently. Water's ability to store heat stabilizes temperatures, feeding the atmosphere steadily rather than in pulses. Winds passing over warm water pick up moisture continuously, priming the air for cloud formation far downstream. Over cold water, the opposite occurs. Air cools from below, becomes stable, and resists vertical motion. Low clouds and fog often form here, the atmosphere flattened and restrained by the surface beneath it. Mountains introduce another layer of interaction. As air is forced upward over rising terrain, it cools and condenses, producing clouds and precipitation on one side while drying and warming on the other. This is not a special case of weather, but the same physics expressed through topography. Lift creates clouds, descent creates warmth and dryness. The land itself becomes an active participant in atmospheric motion. Even small variations matter. A coastline marks a sharp boundary between land and sea, and each day sunlight exaggerates that contrast. Land heats quickly, air rises, and cooler marine air flows inland as a sea breeze. At night, the pattern reverses. These gentle circulations are driven by the same principles as planetary winds, simply scaled down to human dimensions. Through these interactions, the surface continuously seeds the atmosphere with structure. Weather does not descend fully formed from above. It grows upward from the ground, shaped by what lies below. The physics is intimate. Every patch of terrain nudges the air differently, contributing its own small influence to the larger flow. Above this restless boundary, the atmosphere smooths out. Winds strengthen, directions stabilize, and motion becomes more coherent. Yet the influence of the surface never vanishes completely. Turbulence, moisture, and heat continue to feed upward, ensuring that the sky remains connected to the ground, no matter how high clouds may climb. In this way, weather becomes a dialogue between earth and air. The planet offers heat, water, and resistance. The atmosphere responds with motion, clouds, and rain. Neither acts alone. Each shapes the other through continuous exchange governed by simple physical rules. Standing on the surface, we experience weather as something that happens around us. But from a physical perspective, we are embedded within the boundary itself, living where solid earth and fluid air negotiate their differences. The warmth on a sunny afternoon, the chill before dawn, the gust that bends grass or rattles leaves, all of it arises from this ongoing conversation. The atmosphere does not forget the ground. It carries the imprint of land and water upward, folding those influences into larger patterns. Weather, at every scale, remains anchored to the surface, translating the physics of heat, motion and matter into the endlessly varied conditions that surround us, moment by moment, without pause. The atmosphere does not reset from one moment to the next. Every state of weather carries with it a memory of what came before, encoded in temperature gradients, moisture distributions, and momentum already in motion. Air that was warmed yesterday may still be aloft today, drifting far from where it first absorbed energy. Moisture evaporated from an ocean surface can remain suspended for days, traveling across continents before returning as rain. Weather unfolds not as isolated events, but as a continuous physical history. This memory exists because air has mass and motion. Once set in motion, it does not stop instantly. Winds persist because momentum must be transferred or dissipated. Warmth lingers because heat escapes, gradually through radiation and mixing. Even clouds leave traces behind, shading the surface, altering evaporation, and modifying the thermal balance below. Each process feeds into the next, ensuring continuity. Time enters the physics through delay. Energy absorbed at the surface does not immediately leave the system. Oceans store heat across seasons. Soil moisture influences evaporation weeks later. Snow cover alters reflectivity long after a storm has passed. These delays stretch the atmosphere's response, smoothing some variations while amplifying others. Weather today is shaped by sunlight from earlier days, by winds that have curved and stretched over distance, by surfaces that have remembered heat or cold. This persistence is why patterns can emerge. A blocking high-pressure system may linger for days because the air within it is warm, dry, and resistant to change. Jet streams can maintain their paths because strong temperature contrasts at altitude continue to feed them. Droughts and wet periods are not accidents, but extended expressions of energy imbalance held in place by feedbacks that reinforce themselves. Yet memory does not mean rigidity. The atmosphere remains flexible, responsive to new inputs. A change in sunlight angle, a surge of moisture, a shift in large-scale flow can gradually erase old structures and write new ones. Weather balances between persistence and change, between what has been stored and what is arriving. At night, when the surface cools, the atmosphere responds again, forming new layers, shifting winds and redistributing heat. Morning sunlight reverses some of those changes, but not all. The day inherits the night, just as the night inherits the day. This continuity gives weather its rhythm, its sense of progression rather than repetition. On longer timescales, this same physics underlies climate. Average patterns emerge because the same energy flows recur year after year. The details vary endlessly, but the constraints remain. The planet's tilt sets seasons. Rotation sets circulation. Composition sets how radiation is absorbed and emitted. Weather dances within these boundaries, free to vary, but never free to escape the rules. Living within this system, we often focus on immediacy. Will it rain today? Will the wind pick up? Will the temperature drop by evening? Physics sees a broader arc. Each of these outcomes is the latest expression of motion already underway, shaped by what the atmosphere remembers and what it is being asked to adjust to next. This perspective softens the sense of unpredictability. Weather is not impulsive. It does not arrive unannounced. It develops through accumulation, through the slow shaping of gradients and flows. Sudden changes feel sudden only because their preparation occurred beyond our notice, higher up, farther away, or earlier in time. The sky overhead, then, is not just a snapshot. It is a moving record. Clouds trace rising air that has travelled from the surface. Winds carry signatures of distant pressure differences. Temperature reflects exchanges that may have begun days ago. Every moment of weather contains within it a layered history, written in motion and heat. Understanding this does not make the atmosphere feel distant or mechanical. It makes it feel continuous. The air around you has been elsewhere. It has been warmed, cooled, lifted, mixed, and shaped before arriving where you are. You are breathing part of a story already in progress, one that will continue long after this moment passes. In this way, weather becomes time made visible. Physics unfolds not only across space, but across duration, linking moments together through cause and effect. The atmosphere remembers just enough to remain coherent, and forgets just enough to remain free, balancing continuity and change as it carries energy forward, minute by minute, across the turning Earth. As energetic as the atmosphere can become, it almost never reaches its theoretical extremes. Physics places limits on how fast winds can blow, how tall storms can grow, and how much heat the air can hold at once. These limits emerge naturally from the same processes that drive weather in the first place, acting as quiet governors that prevent runaway behavior. Consider rising air within a storm. As long as the air inside remains warmer and lighter than its surroundings, it will continue to ascend. But with height, the surrounding air grows colder and thinner, and eventually the rising air spreads out beneath the stable layer above. Energy that once fueled vertical growth is redirected sideways. The storm reaches maturity not because it is finished, but because the environment no longer supports further ascent. Wind behaves similarly. Pressure differences accelerate air, but friction, turbulence, and curvature all act to redistribute that momentum. As winds strengthen, they mix air more vigorously, smoothing out the very pressure gradients that created them. Strong winds contain the seeds of their own moderation. The faster the flow, the more efficiently it erodes the imbalance that sustains it. Moisture, too, carries limits. Warm air can hold more water vapor than cold air, but once saturation is reached, additional moisture condenses and falls out as precipitation. Rain and snow remove water and energy from the system, cooling the air and stabilizing it. In doing so, they weaken the processes that made them possible. A storm rains itself out not as an ending, but as a natural consequence of energy release. These feedbacks do not eliminate extremes entirely, but they constrain them. Hurricanes draw strength from warm ocean surfaces, yet they weaken when they move over land or cooler water. Heat waves intensify under clear skies and sinking air, yet they are eventually disrupted by shifting circulation or cloud formation. Cold outbreaks persist when snow reflects sunlight and reinforces cooling, but they too are bounded by energy arriving from elsewhere. The atmosphere is therefore not a system that escalates indefinitely. It oscillates within ranges defined by thermodynamics and motion. Extremes occur when multiple factors align, when energy input, moisture, and structure reinforce one another. They fade when those alignments loosen, not through intervention, but through physics redistributing what has accumulated. This boundedness gives weather its texture. If storms always intensified without limit, the atmosphere would be hostile and unstable. If limits were too strict, motion would be weak and uninteresting. Instead, the system balances near thresholds, capable of drama but inclined toward moderation over time. From within this balance, weather feels expressive. A sudden downpour, a powerful gust, a rapid temperature drop. Each is intense on human scales, yet modest compared to what physics would allow under different conditions. The atmosphere explores its possibilities carefully, constrained by energy availability and the geometry of the planet. These limits also shape how weather feels familiar. Storms have recognizable forms. Winds follow preferred paths. Clouds adopt recurring shapes. Patterns repeat not because the atmosphere is repetitive, but because the governing physics channels variability into certain expressions more easily than others. Familiarity emerges from constraint. Over long periods, this same bounded variability gives rise to averages. Climate reflects the envelope within which weather moves. Extremes press against that envelope, revealing its edges but rarely escaping it. When the envelope itself shifts, Through changes in energy balance or composition, the character of extremes shifts as well. The physics remains the same, but the context changes. Understanding limits does not diminish the power of weather. It clarifies it. A storm is powerful precisely because it operates near thresholds, converting stored energy into motion efficiently. Its strength lies not in excess, but in coordination, in many small processes aligning long enough to produce a coherent result. Standing beneath such events, it can feel as though the sky is testing boundaries. In truth, it is revealing them. Each extreme traces the contours of what is possible, sketching the shape of the physical rules that contain it. When the wind eases and the rain fades, the atmosphere has not failed. It has completed an adjustment. Through all of this, the atmosphere remains responsive rather than volatile. It adjusts continuously, correcting imbalances, redistributing energy, and settling into new configurations that reflect current conditions. Weather rarely goes all the way because it does not need to. Balance is restored long before the edges are reached. This restraint is part of what makes weather livable. Motion without collapse, energy without excess, change without rupture. The sky above expresses the laws of physics not as absolutes, but as tendencies, gently enforced, quietly, persistent. And so, each day's weather unfolds within a space of possibility shaped by limits as much as by drivers. Sunlight arrives, air responds, motion grows, peaks and relaxes. The atmosphere never seeks extremes for their own sake. It seeks balance, again and again, expressing that search through the endlessly varied, yet always bounded patterns we experience as weather. Seen from far enough away, Earth's atmosphere behaves like a vast heat engine, quietly converting energy from the sun into motion before releasing that energy back into space. This framing is not metaphorical in a loose sense. It reflects the same physical principles that govern engines of any kind. Energy enters at a higher temperature, moves through a working system, and exits at a lower temperature. The work done along the way is the motion of air and water. Sunlight warms the surface most strongly in the tropics, creating a reservoir of high-energy air and water vapor. Farther toward the poles, energy is lost more readily to space, creating cooler regions. The atmosphere exists between these extremes, transporting energy downhill along this temperature gradient. Wind, storms, and circulation are the work performed as energy flows from where it is abundant to where it is scarce. In this engine, warm air rises in the tropics, carrying heat upward. As it moves poleward at altitude, it cools and eventually sinks in subtropical regions, forming broad zones of high pressure. From there, air returns toward the equator near the surface, completing a circulation loop. Similar loops operate at higher latitudes, each shaped by rotation, moisture, and geography. These cells are not rigid machines, but flexible patterns that adjust continuously. What makes the atmosphere unusual as an engine is that its working fluid is also its structure. The same air that transports energy also defines the pathways along which energy moves. When those pathways shift, the engine reconfigures itself. A change in temperature contrast strengthens or weakens circulation. A redistribution of moisture alters where energy is released. The system adapts without gears or pistons, guided only by physics. Efficiency in this context does not mean speed or intensity, it means balance. If energy were transported too slowly, temperature differences would grow extreme. If transported too aggressively, gradients would flatten and motion would weaken. The atmosphere finds a middle ground, maintaining enough imbalance to sustain circulation while preventing runaway contrast. Weather is the visible evidence of this balancing act. Storms represent moments when the engine operates locally at high intensity. Moisture concentrates energy in specific regions, allowing rapid vertical transport. Heat that might otherwise drift slowly poleward is lifted quickly upward and outward, then radiated to space or spread across latitudes. In this sense, storms are not failures of balance but tools of it, enabling efficient adjustment when conditions allow. Rotation complicates this engine without breaking it. The Coriolis effect bends flows, preventing direct paths and encouraging circular motion. This reduces efficiency in a narrow sense, but increases stability. Energy still moves, but along curved routes that distribute momentum more evenly. The result is a system that is robust rather than optimized, resilient rather than extreme. Over oceans, the engine gains a flywheel. Heat stored in water smooths variations, feeding the atmosphere steadily. Over land, rapid heating and cooling introduce pulses, sharpening contrasts and promoting variability. Ice and snow reflect energy away, altering gradients. Vegetation mediates moisture flow. The engine responds to each of these influences, recalibrating continuously. What emerges is not a machine striving toward an endpoint, but a process that sustains motion indefinitely. As long as sunlight arrives and Earth radiates energy back into space, the engine runs. There is no finished state, only ongoing adjustment. Weather is not the output of the engine so much as the engine in motion. This perspective reframes calm conditions as well. A clear, still day is not an idle engine. Energy is still entering and leaving, but the gradients are weak, the pathways gentle. Motion occurs at scales too subtle to notice easily. The engine idles, conserving structure while remaining ready to respond. From within the system, these distinctions feel qualitative. Calm versus stormy, warm versus cold. From a physical standpoint, they differ only in degree. The same rules apply, the same flows connect them. Weather's variety reflects how many ways energy can move through air and water under constraint. Understanding the atmosphere as a heat engine does not strip weather of its immediacy. It deepens it. Each breeze becomes part of a global circulation. Each cloud participates in energy exchange between surface and space. Each shift in wind direction reflects a subtle rebalancing somewhere else on the planet. Living beneath this engine, we experience its motion locally, one moment at a time. Physics sees the continuity. Energy arrives from the sun. It moves, transforms, and departs. The atmosphere carries out this task with remarkable subtlety, expressing the same fundamental process through endless variation. Weather, then, is not merely changeable conditions overhead. It is the planet breathing energy through air and water, converting light into motion, motion into balance, and balance into the shifting skies we live under. The physics does not hurry. It does not hesitate. It simply continues, turning sunlight into wind, clouds, and rain, moment after moment, as long as Earth remains bathed in light. When all of these pieces are held together, weather reveals itself as something quietly coherent, not a collection of events, not a series of surprises, but a continuous physical response to energy moving through a rotating world. Sunlight arrives, the surface absorbs it unevenly. Air responds by rising, sinking, curving, and flowing. Water carries energy invisibly, then releases it again. Motion organizes itself, adjusts, and relaxes over and over. Nothing in this process is rushed. The atmosphere does not seek drama. It seeks balance, and it achieves that balance through motion because motion is the only option physics allows. Wind is not a disturbance layered on top of stillness. It is the natural state of air when energy is uneven. Clouds are not decorations in the sky. They are markers showing where air has risen, cooled, and changed phase. Rain is not an interruption. It is energy completing a circuit. From this perspective, weather becomes less something that happens to you and more something you are inside of. The air around you has traveled, carrying with it heat from one place and releasing it in another. The temperature you feel reflects exchanges that began hours or days ago. The sky above is not blank or random. It is structured, layered, and responsive, shaped by forces that remain steady even as outcomes vary. This steadiness is what allows calm to emerge from understanding. When the wind shifts, it is because pressure has adjusted. When clouds thicken, it is because air has risen and cooled. When a storm fades, it is because the energy that sustained it has been redistributed. There is no need to assign intention or conflict. Physics is sufficient. Even unpredictability fits gently into this picture. The atmosphere is sensitive, not unstable. It reacts to small differences because it is fluid and connected, not because it is fragile. The same sensitivity that limits long-range forecasts is what allows the system to respond efficiently to change. Variability is not a flaw, it is a feature of motion under constraint. Seen this way, weather is not noise layered on top of climate or physics. It is physics expressing itself in real time, translating abstract principles into sensations you can feel, warmth on your skin, cool air moving past your face, the weight of humid air before rain, the clarity after a front has passed. Each is a physical statement made visible and tangible. As this understanding settles, the sky no longer needs to be decoded or predicted perfectly to be appreciated. It can simply be noticed. Patterns reveal themselves quietly. Changes feel less abrupt. The atmosphere becomes a companion system rather than an adversary, doing exactly what it must with the energy it receives. And so, weather continues. Not toward an ending, but through a steady sequence of adjustments that never truly stop. As long as sunlight reaches Earth and the planet radiates energy back into space, air will move, clouds will form, and the sky will remain alive with motion. For now, that motion carries on above and around you, layered, balanced, and patient. Physics does not hurry it along. It allows it to unfold at its own pace, moment by moment, turning light into wind, wind into clouds, and clouds into the ever-changing conditions we live within. The atmosphere keeps working, quietly and reliably, and you are free to simply rest inside that understanding, knowing that every shift in the sky is part of a larger, steady order that has been unfolding long before this moment and will continue long after it passes.